This is the second section of chapter 19, uh, basically the types of reactions, part 2. And so before we can talk about that, though, we need to talk about this chart that you have in your packet. Basically, what the last chart that we haven't discussed, it's called the solubility chart. Looks kind of wild and crazy, but actually, once we kind of talk about how to use it, it's not as difficult as what it might look at first. So the solubility chart basically discusses like how soluble something is, meaning will it dissolve in water or not. And so basically, how this is set up is that the column, meaning the up and down here, are your positive charges, meaning the first element in your compound. The row going across here are your negative charges. And so, for example, you might be given a compound like, let's take basic table salt. So, like NaCl, okay, or we know that as sodium chloride. So, what you would have to look up, let's kind of get rid of this stuff over here a little bit. So, what you would have to look up is sodium. So, you would go over here. You would look up sodium, so I would find sodium in the positive column, because I didn't really highlight very well. So I'd look up sodium, and then I would look up chloride in my top column, and basically you would bring your fingers together until they meet, and you will see that when you do that, you have an A. Now, A stands for aqueous. What aqueous means is that it's dissolved in water, which means that you would find it in ion form, meaning that when we do a reaction, it won't precipitate out, meaning that you would not find it in, as you notice, a lot of these you would find little S's, like for example, this one, mercury 2 hydroxide, is a solid, and so it's a solid. And so that's a precipitate, meaning that when I mix some chemicals together and I get mercury 2 hydroxide, I get an actual solid produced. And so that precipitates out. So, and you'll see that when we do a lab. You'll get, when you mix things together, you get something that precipitates and something that does not precipitate. So in this case, sodium chloride is aqueous. So that would not result in a solid. Whereas mercury 2 chloride, it would be a solid. You would get this chunky something substance in the bottom. Okay? So when we do our first type of reactions, which in this section we're focusing on double displacement and combustion. So when we do our double displacement reactions, we're going to need that solubility chart to label our products. So double displacement reactions are when you get a positive ion of one compound and it replaces the positive ion of another compound. So it's totally replacing, we're having a double switcheroo, hence we're double. Okay, and so it'll take place if a precipitate, a water, or a gas is formed. And we're going to talk about that a solid is a precipitate. You're going to use that solubility chart as we already talked about. Here's kind of an example of what happens just in the generic form in the sense of an equation. What happens is that you have a compound AB, you have a compound CD, and if you notice, all that happens here is that they basically break up. A, who was originally with B, is now with partner D, and C, who was originally with partner D, now hooks up with B. So basically they are breaking up and switching partners. So kind of just to even show you this in a visual form again, A and B break up, C and D break up, A now hooks up with D, B hooks up with C. And I guess you have to do it the other way. C has to hook up with B. Okay, so that's what you'll be doing. You'll be breaking up couples and making new couples. Okay, so let's actually look at that. Example number 1. Alright, so silver nitrate, So we have silver, and I should have put a 1 in there, I guess, for you guys. Alright, so that should be AgNO3 when I make the formula, plus sodium chloride, NaCl. Alright, so when this breaks up, what's going to happen here is that silver makes a 1 plus charge, NO3 makes 1 minus charge. All I did was take that original compound, figure out what the charges are. Same thing with sodium and chlorine. I break it up. I just wrote down the elements, figure out the charges. Now, silver is a positive charge. Silver was originally hooked up with the negative charge of nitrate. It broke up with nitrate. Doesn't like nitrate. Doesn't want to be with nitrate anymore. So now it's got to go with a new negative charge. Its only option is chlorine. So it's going to hook up with chlorine. So Ag with a 1 plus charge is now going to hook up with chlorine with a 1 minus charge. So if we cross those charges, we get AgCl. We're going to add that to the next positive charge, which is sodium. Now, it broke up with chlorine. It needs to go with someone new. So it's going to go with the nitrate ion. So Na is going to go with NO3. Cross those charges. NaNO3. So basically, if we kind of define what we just did, 1, break all compounds into ions. Okay. All right. And then number 2, make new partners. Kind of side note, the positive is always first. Okay. Then of course we need to balance our equation. In this case, it's already balanced, so I don't need to do anything with it. And then last but not least, we need to check solubilities. Meaning we need to look at our chart and we need to determine, and you'll only need to check, and I guess I should put check solubilities of products. Because the solubilities of the reactants are always going to be assumed to be aqueous, because you're going to be able to break those down and make products. So we're assuming they're in ion form. So the only thing you need to check on are the actual products. So in this case, we're going to look up AgCl. So you're going to use your solubility chart. You're going to look up silver. You're going to look up chlorine. You're going to bring your fingers together, and you're going to determine that that's a solid. You're going to do the same thing for NaNO3, and I kind of ran out of room, so I'll just kind of stick it in here. You're going to determine that that is aqueous. Okay, and that needs to go in there next to the 3, but I ran out of room. Okay, so those are all the steps that you need to do. We'll go through another one. And the funny part is, on a video I still about said, are there any questions? There's nobody in the room. But do you have any questions? Answer me anyway. Answer the screen. Alright, number 2. Copper 2 sulfate. So you have CuSO4 plus sodium sulfide Na2S. And I'm going very quickly writing these formulas because it's pretty much assumed that so far you should be able to write formulas. Alright, so breaking these into ions, I have Cu with a 2 plus charge and SO4 with a 2 minus charge. And maybe going through this, you'll see how I got the original formulas. Na with a 1 plus charge, S with a 2 minus charge. Now, okay, so copper has a 2 plus charge. It was originally hooked up with the negative charge of the SO4. Doesn't like the SO4 anymore. So it's going to now go hook up with the other negative charge possible, which is the sulfur. So we're going to hook up Cu with a 2 plus and S with a 2 minus. So that's going to result in CuS. Sodium now, the positive charge needs to hook up with a different negative. Its only option is the sulfate. So, sodium that has a 1 plus charge is going to hook up with the sulfate that has a 2 minus charge. So, that's going to make a product of Na2SO4 and so there are your two products. Now this equation will need some balancing, I believe. Let's see. Cu, good. SO4, good. Na, good. Oh, I lied. Sorry. We are balanced. Okay. Now, so we're balanced. And then, so now all we just have to do is check for solubility. So, CuS, so copper and sulfide. So that's a solid. And then sodium sulfate. Okay, so sodium sulfate, we looked that one up. That one should be aqueous. Now, here's a little hint too I didn't bring up in the previous video. Pretty much every combination of solubilities is fine, except for you will never get two solids put together. Okay, that does not happen. So you can get aqueous, you can get solid and aqueous, but you cannot get two solids. So if you end up with a product of two solids, you've messed up somewhere. Okay? Alright. Number 3. And really you should be getting to the point on this point in the video where maybe you're pausing and you're trying this on your own. Okay? So we have, so I'll go maybe a little faster on this one and you can kind of just do it on your own, check it. So we have was a little larger than what I meant it to be. Alright, so we have Fe, let's see, so Fe NO3, 2, plus NH4, 2S. So a little bit more complicated though, because it has some polyatomics. Still break it down. Fe with a 2 plus charge, NO3, 1 minus charge, NH4, 1 plus charge, S with a 2 minus charge. Okay. Now, so you're going to take the iron, you're going to put it with a new negative. Okay. So that's going to make it so that you have to put Fe with a 2 plus, sulfur 2 minus. So those are going to reduce, so you just get FeS. Decided to write big this time, sorry. Alright. And then the ammonium is going to go with the nitrate. So you have NH4, 1 plus is going with the NO3, 1 minus. You're crossing ones down, so it's just going to be NH4, NO3. So there are your two products. Now, so there are your products. You need to make sure that this is a balanced equation. So to balance this, let's see, I have 2 NH4s and 2 NO3s, and so that took care of it, just putting a 2 there. Solubilities, so I have to look up iron 2 sulfide. That's a solid. And I have to look up ammonium nitrate, and that one is aqueous. Okay, so there we go. Last but not least, this is an example of an acid-base reaction. Okay, because you have HNO3 and it starts with an H, so that indicates you have an acid. And then you have NaOH, which it ends in an OH, which indicates that you have a base. So this is an acid-base. An interesting thing about acid-base reactions is that when we go to break this down, we have hydrogen, we have NO3, Na. Now, acid-base reactions are still part of the double displacement category. It's just, you're not going to get a solid. I guess you can. You can get, I'll rephrase that. You can get a solid, but you're also going to get a different product. Okay, so here are your ions. You have hydrogen. Hydrogen is going to go with a new one. It's going to go with OH. So, H is going to go with OH. So, technically it produces HOH. But look at how many hydrogens you have. You have 2. So, technically this is the same thing as... So, what you need to do if you have a hydrogen ion going with an OH ion, you need to write that as water. So one of the products of an acid-base reaction is water. So the production of an acid-base reaction, one of the products is water. And actually the other one is a salt. And a salt is just a generic word for an ionic compound. And an ionic compound is just anything that was formed by ions. So for example here, I have sodium is hooking up with NO3. So Na with a 1 plus is going to hook up with NO3 with a 1 minus. So I have Na NO3. So that was formed, that sodium nitrate was formed by ions. So that is an example of an ionic compound. So NaNO3 is technically a salt. So we have salt we put on our French fries, which is NaCl, which is classified as table salt. We have road salt, which is a mixture of different salts, but mostly calcium chloride. So it's just a common term. So we have water and salt is our products. Now this equation is already balanced. Now to label it here, we still look up the solubility of your ionic compound. So the NaNO3 is aqueous, but your water, what's the most common form of water? Liquid. So that's how we're going to label it. And there you're done. So that's double displacement reactions. We're going to do lots of practice with that and hopefully get you, feeling comfortable with those.